next one, that is variable partitioning scheme. Okay, so let us start with the next one. From here only we will start, because multi-programming with variable partitioning scheme, with variable, or we can say dynamic. Okay, without dynamic partition. Okay, so multi-programming with variable or dynamic partitioning. Okay, we'll start with this one. This is also very simple. Let us start with this. The main problem with the fixed size partitioning is the wastage of memory. What we have seen in the earlier one, if we are placing any process, for example over here, you can see in this example only, in the unequal size partitioning, what we have done, we have placed the process third inside fourth partition, which was of 8 KB. So it requires only 7 KB and the 1 KB space was unused. Okay, so the wastage of memory was there in the fixed size partitioning or fixed partitioning scheme. The main problem was wastage of memory. Okay, and it was due to the internal fragmentation. Okay, so a different memory management approach known as the dynamic partitioning. Now we have a dynamic partitioning scheme. So we have a new partitioning scheme, that is dynamic partitioning scheme we have to use. Okay, and this is also called variable partition also. Okay, variable partitioning or dynamic partitioning scheme, you can call both of them. So variable or dynamic partition. Okay, in dynamic partitioning scheme, what it will do, it create partition dynamically. Okay, so it create partition dynamically. Now how this will create a partition dynamically, we'll see. To meet the requirement of each requesting process, to meet the requirement of each requesting process. Okay, to meet the requirement of each requesting process. Okay, so if the process is coming with 7 KB, then we will allocate the memory of 7 KB only. Okay, we are not going to allocate the memory, or we are not going to create the partition at the system generation time. Okay, so we will create the partition according to the requesting process. Okay, according to the requirement of each requesting process. Okay, so when a process terminates or becomes swapped out, the memory manager can return the vacated space to the pool of free memory. Okay, when memory become free, it is added to the pool of memory. Okay, it is added to the pool of memory. Now here memory manager continues creating and allocating partition to requesting processes. Okay, so our memory manager is continuously creating the partition, and after that it is allocating them. Okay, so memory manager continues creating and allocating partition, continues creating and allocating partitions to requesting processes until all physical memory is exhausted. So allocating partition to requesting processes to requesting processes until all physical memory is exhausted. Okay, so what is happening in the dynamic partitioning? We are not creating the partition at the starting only. Okay, so we will create the partition, we will generate the partition according to the requirement of each requesting process. Okay, and our memory manager is the one who continuously creating and allocating the partitions to the requesting processes until all the physical memory is exhausted. Okay, we'll see with the example. This is the very good example. You can easily understand how it is working. So this is the main memory. Right now we are having, this is the main memory. Okay, so we have operating system over here, okay, and this is the user space. Okay, this is the user space. So we have allocated, I think suppose we have allocated 120k to the operating system, and the remaining 896k is remaining right now. Okay, now process 1 will come. Okay, after this the process 1 will come. Process 1 is having a requirement of 200 kb. Okay, say 320 kb. So this is second diagram. This is for the OS which requires 128k. will not add again. So process 1 is coming. We have created first partition because processor 1 wants 320k. Okay, so process 1 has entered now. Okay, so now the remaining memory is 576k. Now process 2 will come. Okay, process 2 required 224. So 320 kb for process 1, for process 2 224k. Okay, so the remaining is 352k. Again process 3 will come. So process 3 is over here. Process 3, this is for OS. Again this is for OS. We have a process 1, we have a process 2. Process 3 will come. Process 3 required 288k. Okay, 224k, 320k, and this is for the OS. Okay, and so now we are having 64k remaining. This is 64k remaining. Okay, now try to understand. These all are the diagrams. Diagram A, diagram B, diagram C, and diagram D. What is happening in the dynamic partitioning? Okay, in dynamic partitioning we are creating the partition according to the requesting process. Okay, in the first diagram you can see we are having the whole user space empty of 896 kb. Okay, we have only allocated 128k to the operating system. After that process 1 comes. So process 1 was requesting 320k. So we have given 320k to the process 1. The remaining is 576k. Now the process 2 will come. It required 224. So we have created according to the requirement, according to the requesting processes. Okay, so we have given 224. The remaining is 352. Okay, then process 3 come. We have given 288k and the remaining is 64k. Okay, so we have created the partition according to the requesting processes. The operating system keeps a table indicating which parts of the memory are available and which is occupied. This is very important point. This is the operating system which keeps track of OS. Keep a table of free and occupied memory. Initially, all memory is available for the user processes and is considered as a one large block. You can see this is the whole large block. After allocating, it remains this one. After allocation, it one. And after allocation, the last remain is 64k. Okay, the idea of the variable size partition allows the operating system to create partitions of exactly the right size for the particular process. So partition creating partition of right size, okay. The right size for the particular process whenever there is a sufficient space available, okay. And the very important point over here is internal fragmentation we have removed. Internal fragmentation is eliminated. Okay, you can't see any space which is over here, but there is a space in the last one. So maximum we have eliminated the internal fragmentation. But there is another problem, okay. But there's a new problem emerges. Processes are initially added to the system using continuous memory space. Each process complete, however, it is removed from the system, leaving a hole in the memory. Okay, now what is happening? Just look into the matter. Just try to understand. Okay, we have a new problem now. Now, what is the problem? The problem is that you can just imagine this one. Okay, after diagram D, we'll consider the next diagram. This is again main memory. Okay, process 1 has completed. Okay, imagine process 1 has completed. It took 320k memory. Okay, so it was OS. Okay, and this is, so process 1 has completed, process 3rd has completed. Okay, process 2 is still running, so process 3 is still running. This is 64k which is still empty. Okay, process 2 is still running, process 1 has completed, process 3rd has also completed. So they have completed this 320k memory, and this is the 288k memory. These are called as holes. Because now when any other process who wants to come and execute, then there is very less probability that the process which is coming over here for execution is having exactly same requirement, that is 320k and 288k. So they are called as whole. Suppose a process 4 has arrived now. Okay, process 4 has arrived, and process 4 is having a requirement of 280k. Okay, so we'll draw the another diagram. Okay, this is for OS. So process 4 has arrived, process 4 requires only 280k. So first we'll draw the raw diagram. Okay, so this is of 320k, we'll leave it. This P2, this is empty. Okay, so P4 has arrived, and P4 is having a requirement of 280k only. So P4 is using only 280k. P4 is using only 280k. Okay, if they are using 280k, then 40k is remaining over here. Okay, so 40k is remaining, and this 40k remains as it is only. Process 5 comes over here. Okay, process 5 is having a requirement of only 200k. Okay, so process 5 comes over here. So process 5 comes over here. It is using 200 from the 288k, and the remaining 88k will be unused. These are called as whole. These are called as holes. Okay, so this is the new problem in the variable partitioning scheme. Okay, are you getting my point? What are the called as holes? These are called as holes. Okay, after allocation of new processes, after allocation of the new upcoming processes, the remaining space, the remaining memory, which is over here, you can see this is the hole and this is the hole. Okay, so this, it can be called as a hole. Okay, so what we have to do, we have to manage it properly. Okay, if we will manage it properly, then it will be very easy for us to easily tackle it. Okay, and how to tackle it, how to manage these whole, and how to do this how to do the management of this properly. This is a very essential task, and we can do it using the memory placement algorithm we are having in the next video. Okay, thank you so much.